equation. It's this lemma that says that if f prime is positive on an open interval I, then f is increasing on I. Then f is increasing on I.
Is lemma like a dilemma or?
I think they're related. Lemma just means like in math, lemma just means a small theorem, sort of like a theorem that you use, a small result that you use to get to something bigger. So it's like a tool, basically. But a dilemma, right, is something where you have a choice between two things and you're sort of stuck between them, right? I'm not sure exactly how that relates to the word lemma. If your function is increasing on an open interval, then your function, if your function has a positive derivative on an open interval, then it's increasing on that interval. This is actually a consequence of the very important mean value theorem that we talked about last time. Just to remind you what increasing means, right? Increasing means that if you have 2 points, right, x and y, then and x is less than y, then f of x is less than f of y. So that's what increasing means. Right. Let me see if you can figure this out. Let me see if somebody can give me an argument using the mean value theorem. This is actually really similar to something we did last time. So, why is this going to happen? Take a minute or two, take 1 minute and see if you can figure out like how one uses, how this follows from the mean value theorem. I think you might be able to do it. Maybe I should give a prize for it. 2 points on the next one if you get it. Okay, anyone have an idea? Anyone have an idea? Anyone have any slight idea? Feel free to raise your hand. Rachel first.
So, I don't have much of a voice, so sorry, but
That's all right.
the average slope that you find using the mean value theorem in between them needs to be positive for increasing, so fy minus fx.
One makes sense.
Would be positive.
Why is it positive?
Well, so you look for a point in between them that has the average slope, but like all the points in between them.
Wait,
No. So you use the mean value theorem to look for a
the
point
mean value theorem
between
says,
them.
so if there's some point between x and y where
F prime of c is equal to but that would be positive.
But this is positive, right? You know, you're given that f prime is positive everywhere, right? You're given that f prime is positive everywhere, and so what?
So that the slope is, so that those points have y and fy has to be greater than fx and y has to be greater than x for that slope to be positive.
Okay, well, y is already greater than x. So this is positive.
But
So that tells you that.
the fy has to be bigger than fx.
Right. So this has to be positive too, right? In order for this ratio to be positive. Let me write it down. Okay, great job. So well, look, why is this true? Why? The mean value theorem says there is some point where, so there is some point between, given 2 points x and y, and x is less than y, the mean value theorem says that there exists a point in f1 where f prime c equals f of y plus f of x over y minus x. Right? But we know f prime c is positive. F prime c is positive, right? Because we know that f prime is positive everywhere. Right? F prime is positive, and of course y minus x is positive. Right? So that tells you that f of y minus f of x is also positive. Right? In other words, f of y is bigger than f of x. Right? So whenever you have 1 point, whenever you have 2 points, the one on the right always has the greater value. In other words, your function is increasing. Given any points, you know, one on the left, one on the right, the one on the right always has a bigger value. The function is increasing. Okay, good job, Rachel. Eliza, did you have that?
Yeah, kind of similar.
It's kind of similar. Okay. Maybe I should give you points. Okay. Okay, yeah. Okay. And similarly for decreasing functions, right? If your function is if your derivative is negative on an open interval, then your function is decreasing on that interval. Okay. So application. Let's consider the function f of x being x cubed plus 3x squared minus 4 plus x plus 2 on the real line. And I'd like you to answer these questions. Where are possible extrema? Where is it? Where is f increasing? Where is f decreasing? So, take 1 minute and see what you can get. See what progress you can make. And then I'll go outside again. I think you all talk more to each other when I'm outside.
So that's how you find this from. Yeah.
Do you know the point between there was? Or
There shouldn't be 6.
okay. So what do we need to do? If we're looking for possible extrema, how do we do it? What do we need to do? Set the derivative equal to 0, right? So when we're looking for extrema, right, the procedure is basically look for where f prime doesn't exist. F prime, so f is not differentiable, or f prime is equal to 0. Where f prime is not differentiable or f is equal to 0. These, because one often looks for these sort of places, they give this sort of thing a name. It's called a critical point. Critical point, where the derivative doesn't exist or where the derivative is equal to 0. But that's only used in this game of finding the extrema. Anyway, if you understand Fermat's theorem, then you know what to do. Look for where the function is not differentiable or f prime is equal to 0. So you take f prime. You get 3x squared plus 6x minus 45. Right? You factor x squared plus 2x minus 15. Right? And then you get 3x plus 5 minus 3. So you know where it's going to be 0. Right? This is 0. F prime is 0. F prime exists everywhere. F prime equals 0 at x equals -5 or x equals 3. Right. Okay. And then for the second part, right? So those are the possible places, right? And second part, you know, how do you find where f is increasing or decreasing? What do I need to do? Somebody spell the whole thing out for me, Mike.
You look at whether, f prime of x is positive or negative.
Okay, so we know it's 0 at -5 and 3, right? If we're looking at f prime, 0 at these places, right? And where is it positive?
Like above 3. And then it's negative between -5 and 3. And then it's positive.
Right.
So,
Right. Okay. So it's increasing here, right? Between negative infinity and -5 is increasing, right? So f, this tells us about f prime. F prime tells us about f, right? F is increasing on negative infinity to -5, and also on 3 to positive infinity, and it is decreasing on -5 to 3. So the function is increasing up until -5, and then it starts decreasing, right? And then at 3, it starts increasing again. Right? Okay. Yeah, check.
Did you plug the x values into f of x or f prime of x?
You mean, what am I doing here?
Yeah, right there.
Right here, we're looking at f prime. Right? This is f prime here. Right? F prime with 0 at these points.
yeah.
And then, you use your pre-calculus knowledge to understand that it's going to be positive here, negative here, and positive here. Right? I mean, you can either do it by plugging in points. Those of you who maybe forgotten about this, right? You can check because it's a continuous function. Because it's a continuous function, you know that once it crosses 0, it's going to stay above 0. Right? So you just need to check a value over here, and that'll tell you if it's positive or negative. Right? Same thing here, right? You can check a value and say, okay, between -5 and 3, I'm going to check it at 0. I get a negative number, so I know that it's always negative between here. Right? After 3, I'm going to take some huge number, a billion. Right? I get something positive, positive, positive. so it's going to be positive over here, right? Okay. Or alternatively, you say, well, look, I know this thing is a parabola, right? This is an upwards going parabola, so I know it's going to be positive here, negative here, and positive here for f prime. However you do it, you find out that f prime is positive here. In other words, f is increasing here. F prime is negative here, so f is decreasing. And then f prime is positive here, so f is increasing. Okay. So, right, is everyone okay with that? You have to keep straight what's f prime and f, right? Keep that straight. Right? This is f prime, this is not f. It gives you information about f. Okay, so what does that tell you about our possible extrema? Right? Our possible extrema were here and here. Right? These were our critical points. And in fact, we know what they are. Right? What are they? Maya?
Well, since it's f is increasing and then decreasing at -5, it has a local max.
Right. So this is a local max.
And then since f is decreasing and then increasing at 3, it has a local max.
So -5 is a local max, and 3 is a local min. Okay. Right? Because you know that before -5, the function is increasing. Right? The function is increasing. After -5, the function is decreasing. Before -3, the function is decreasing. After 3, the function is increasing. Right? So this allows you to tell what these points are. Okay? Examining the first derivative allows you to classify the extrema, to tell it its extrema. Okay, and so we codify this in a theorem. Right? You can do this in general. And this theorem is called the first derivative test. Here it is. Right? And we're just going to write down what we said, in common sense. So here's the first derivative test. Right? If you have f differentiable on an interval, an open interval, and you know that f prime is 0. If f prime is negative for x smaller than c and positive for x bigger than c, then it's a local, so it would be negative and positive, this will be depending on the local min. Right. If f is positive before and negative after, then it's a local max. Right. If the sign doesn't change, if f prime doesn't change sign before and after, then it's neither min nor max. So this is just a sort of codification of common sense, right? Right. The lemma is all the work, and then this is just an observation. But remember, in order to get the lemma, we needed the mean value theorem, right? And the mean value theorem needed Rolle's theorem. The Rolle's theorem needed Fermat's theorem, and the extreme value theorem. Right? So all these things go back to the very foundations. Extreme value theorem, and the extreme value theorem we don't explain here. We leave that for a much later course. I don't know if I pointed out how you get there, but the much later course is a course called 131. And in general, to get to 131, you have to take linear algebra first. So right now you're calculus 1. So this is a possible route. Like you could go calculus 2, linear algebra, and then to this course, and then you'll finally understand the extreme value theorem. So it's not that hard, to be honest, but that's why we're not going to explain that, because it would take us too far. Okay. In any case, this relies on the mean value theorem, and let's do another example. Find, classify multiple exponent of function f(x) equals x minus sin x. Actually, let's do this one together. So what do we need to do? Of course, you need to take the first derivative, right? And what do I get? 1 minus cosine x, right? Okay. So when am I going to have, when do I have zeros then? When is the first derivative equal to 0? Where are my critical points? 0. Where else? 2 pi, 4 pi, right? Basically any even multiple of pi, right? So 2k pi, where k is an integer, right? Anything of the form 2k pi, where k is some integer, right? The integers, you recall, are things like 0, negative 1, negative 2, negative 2, negative 3, etc. Right? Anything that looks like 2 times some integer times pi. Right? Here's 0, here's 2 pi. This is the cosine function. 2 pi. Right. I'm sorry, we wanted to do 1. Okay, so we want then we want to know where the function is. Right. So wherever cosine is, it could be that I've got something wrong. So here's my picture, right? Cosine function, right? At 0. We're basically looking wherever the cosine function is 1, right? Wherever the cosine function is 1. The cosine at 1 is 1 at 0, 2 pi, 4 pi, etc. Negative 2 pi. Okay. So then what do we need to do? We need to look at the signs of this thing. Right? So right, so this thing 0, 2 pi, 4 pi, 6 pi, blah blah blah. It's 0 at these points, right? F prime is 0 at these points. Right? And then what about the values in between? Shelby? Emily?
It's always going to be, well, that's the top of the thing.
It's always going to be what?
It's always going to be, every value between them is going to be less than them. So,
Every value is good.
Is that what you're asking?
I'm asking, tell me about the signs between these guys. It's 0 at Taylor.
Is it going to be, okay, I make this backwards.
That's right.
Positive, negative, positive. Or
Well,
negative. It switches, right? Negative,
Yeah, so we
positive,
keep switching.
negative.
Well, let's think. Okay. So if we look at the function here's the cosine, 0 to 2 pi. Here. Here's the cosine.
It's all one plus.
Yeah.
Right. Right. So it's always actually it's always going to be positive, right? Because the cosine ranges between 1 and -1. The cosine never gets bigger than 1, right? So you're never going to get a negative number, right? You're never going to get a negative number. You get the zeros when cosine equals 1, these guys. And then in between, you're always subtracting off something smaller than 1, right? You're always subtracting something smaller than 1, right? Something less than 1. Right? So it's always going to be positive, positive, positive. So what does that tell you? That tells you that all these critical points, well, none of them are extrema. So no extrema. Yeah, Rachel.
I'm confused with the picture you drew. Wouldn't there also be a place where the derivative is 0 at pi?
This is the cosine function?
Yeah. So why are we only doing?
It's 1 minus cosine. So you get -2.
Is it okay?
Yeah.
Yeah, Joe, do you have a question? Do you have a question, Joe?
No, sorry.
Okay, that's great. Yeah, Leanna.
I don't understand why there's no extrema. I mean, like, is it because you need to restrict your domain to look at like only one peak and then it would have extrema, or?
Yeah. So I mean, functions need not have maxes and mins, right? It depends. Really, like if we look at just f of x equals x, right? Does it have a max? No. Does it have a min? No. But if you restrict it to it's continuous. So if you restrict it to a closed and bounded interval, then you're guaranteed a max and min. The same thing is happening here, right? We have the function f of x equals x, and we're subtracting off the sine function. Right? The sine function is some sort of is oscillating, right? So you get something like this, right? And then it doesn't. It has they're not even local maxes, right? So no local maxes. Yeah, no local. It's not that it doesn't have global maxes. It doesn't even have local maxes.
Why aren't the peaks local maxes? Like peaky?
They're not peaks actually. They're more like the book has a better picture, but it's something more like this.
Okay.
Right? They're not peaks. Cynthia.
I think like what's confusing a lot of us is that like the graph you drew right on the bottom, it has a piece of in that graph in general it has like maxes.
Okay. This is the problem is again, keep the derivative separate from the function. This is a picture. This is the cosine. Okay, this is the cosine. Let's turn it over. This is the negative cosine. We add 1 to it. This is the derivative right here. This is 1 minus this. Okay. So this is the derivative. No. This is the derivative.
Yeah.
Right? This is not the function. The derivative has a max. That's not saying that the function has a max. You have to keep those things separate. Right? This is the derivative. Right? The derivative. So if somebody gives you this and says, "What can you tell me about the function?" Well, you say, "Well, look, the derivative is positive everywhere." Right? This function doesn't have any max. Right? Yeah. Emily, was that your question?
So is that still going on the second derivative? What is that step located in yet?
This is the original function. This
Oh,
is
1 plus sin. Oh, x minus sin.
x minus x.
Oh, okay, that makes sense.
Rich go.
Well, even though the derivative would be positive, it still changes direction though.
The derivative is positive, yeah.
Yes.
Look at the original.
Like, wouldn't it be changing direction because it's increasing and then decreasing, increasing and then decreasing?
No, so if you graph them both on the same axis, it's a lot easier to see that there are places on the original function where the derivative would be 0, but it's still constantly increasing.
Yeah. Okay, other questions? Okay, let's go on. So, unless you're actually confused about something, let's go. Okay, so, let me, or is anything still confusing about this one? You've taken the derivative, you have your function, right? You have your function, you take its derivative, and you find out that the derivative is a positive function. Well, at least it's not negative,
Oh.
right? Right? This is your derivative, right? 1 minus cosine x. Here it is. Okay. It's positive everywhere. It's 0 every once in a while, right? It's 0, right? The function becomes flat at some points, but it never, right? The function becomes flat at some points, right? The derivative is 0 at 0, 2 pi, 4 pi, blah, blah, blah. But, you know, it never turns around and goes down again. Okay. Okay. So let's try this one. X squared e to the minus x. And this will be the last exercise, and I'll hand out homeworks when you got it.
I just factored out 2x and by this is like negative.
Oh, no, I found the derivative. Let's solve them together after such. And then instead of taking
Yeah, so 0 is equal to x.
I'm both like one couple.
So,
Then you get 2x minus x squared.
you get actually
That's negative 2.
here, right?
Well, how do you
So we're going to divide by x.
x.
It is.
Yeah, then you have to do the natural log. Yeah. What's the natural log of 0?
This is 4, and then the log of x minus 4.
His first time. He's
I forgot.
Maya, is there a natural log of 0?
No, there's a natural log of 1, but I got 0 and 2.
0 to 2.
Okay.
Take the 0 from.
Okay, so you have your function, right? Prime, what's that prime? Is it good?
Negative, oh, should I, okay, negative x squared e, so negative x minus 1 plus 2x e. So I'm doing like order of what kind of
That's correct. That's right.
Did you say, is that what you said? Okay, good. Okay, right, so you take the first guy times the derivative of the second, right? The derivative of e to the negative x is negative e to the negative x, right? And then the derivative of the first times the second. Okay, right? Okay, so then you need to find out where this thing is 0, right? And where it's positive and where it's negative, right? So where is it 0? Or how do you figure that out?
Factor out the x and the unit.
So, right, where's this thing equal to 0? Again, you use the so-called zero product property, right? So this is going to be 0 where either this is 0 or this is 0. Right? If you have a product, the only way that the product can be 0 is if one of the factors is 0. Right? Question?
Yeah.
Yeah.
So couldn't you just like factor out x times e to the minus x and have it x plus 2?
Yeah.
Or x minus 2, sorry.
So you want to, I see. You want to factor out x e minus x,
Yeah.
right?
And then you have x minus 2.
Sure. Right. You can either do it then, or you can do it here.
Because, I mean, if you did that, then you wouldn't get 0 as a critical point. You wouldn't get x equal to 0.
Negative x plus. Right.
It's the same as this
So,
one.
right. So where are the critical points then? 0 and 2.
0 and 2.
So critical points. So personally I prefer to leave it doesn't matter. Same points at 0 and 2. Right? And right, so you know that at 0 and 2, f prime is equal to 0. And what else do you know? What about between them? What about here? Anyone work it up? Anyone? Ellie?
Is it negative, positive, negative?
Negative, positive, negative. And how did you do it? Just out of curiosity.
I plugged in the point, I plugged in like x equals -1.
So you can do it by plugging in points, right? Your function is continuous. You know it's 0 here. So you know it's going to be, consistent sign between these guys, right? Okay. Or again, you could say, I know that this is always positive, right? E to the minus x is always positive, and then here I've got an upside down parabola, right? So I've got this parabola, and I'm multiplying it by a positive number, so I know it's going to be negative, positive, negative. So what does that tell you? That tells you that this one is a min, local min, and this one's a local max. Doesn't say anything about these guys being, notice that the first derivative test doesn't tell you anything about these guys being global. It just tells you about. Okay, that's it for today.